Now let's look at the gains to the summation and difference channel when the signal to noise is very high, and this is in the low noise limit. Then this term is approximately constant, equal to 1, because this is the inverse of signal noise, almost 0. And this term is approximately like this. Multiplying them together and minus 1, we have the gain squared proportional to the inverse of the signal power in each channel. Consequently, the output variance coming from multiplying the gain squared and input power, input variance, is a constant, also because the encoding noise power is a constant. Therefore, no matter whether it's a summation channel or a difference channel, they have the same variance. And when this happens, same variance across different channels, different channels, and this is called whitening. And because O plus and O minus are also decorrelated from each other, and they have the same variance, so the output correlation matrix is proportional to an identity matrix. The same variance in these two channels means the same variance along these axes. That means this distribution is spherical. Yeah. And so in the high signal to noise region, the outputs are not only decorrelated, they are also whitened. The two output channels have equal variance. And this is achieved by having a higher gain to this weaker input channel. When originally it was weaker, we gain it amplified higher. And this serves to enhance the ocular contrast, because this weaker channel is in fact reflecting the contrast between the two eyes. Okay, and enhancing this contrast helps us to see stereo depths, and this is the strategy when the signal to noise is high enough. Let's look at an example with these values of noises and signals. We see that the signal to noise ratio is much larger than 1. And let's first calculate the information available at the input level, and it's a sum of the information in the summation channel and the difference channel. Plugging all these values, you can calculate, it comes to 3.5 bits. Most of it, 2.5 bits of it, is coming from the summation channel as expected. Without the gain control, let's calculate how much information at the output O. And again, you're plugging. Now notice we have the encoding noise and not. And so therefore, the information is slightly less because of additional encoding noise. Not that much less. Okay, it's 3.38 bits. And again, most of it is in the summation channel because this channel has larger signals. Yeah. If we now calculate the cost, and this cost, total cost, is the summation cost and difference cost, the different channels to put together, 362 altogether in arbitrary units. Most of it is spent in the summation channel because it has much more power in it. Yeah. If we now apply gain control, what we do is shrink down the signals in the summation channel by a gain less than 1, but expand the signal power in the difference channel by a gain more than 1. Okay, these values are according to this whitening formula. Okay, and now let's calculate the resulting information in the output. You plug these values in, yeah, plugging all these values. Now it comes to 3.25 bits. Okay, almost the same, a little bit reduced. Okay, even though the information amount in the difference channel actually is increased because its signal power is amplified, although the information amount is slightly reduced in the summation channel. But we can have a look at the cost, and this total cost, again, plugging the values, summation channel, difference channel, the total cost is almost halved from 362 to 185. And most of the savings comes from this summation channel saving, yeah? Even though the difference channel expenditure is increased because the signal power is increased. So therefore, we can see that applying the gain control gives us a much better trade-off between the cost spent and the information extracted at the output level O. In the other extreme, when the signal to noise is very low, the noise dominates. Let's see what happens. The original signal has this ellipsoidal distribution, the variance larger along the summation direction. The noise distribution is spherical because the noise in the two eyes are independent of each other and have the same variance. Adding the signal and noise together, we come to a near spherical distribution when the noise dominates, with a slightly higher variance along the summation direction. With low signal to noise, this factor is just approximately this, since the denominator is dominated by this term. And this factor is approximately like this. And consequently, the gain squared is now higher for the channel with the stronger signal power. And this is the opposite to the case when the signal noise is very high. And therefore, the gain to the difference channel is now weaker. This is a smoothing strategy. We focus on the summation channel, adding the signals from the two eyes together to average out or smooth out the noise, while adding the correlated inputs together to enhance the signal strength. Meanwhile, the contrast signal between the two eyes are abandoned. As a result, the output distribution is now ellipsoidal again, because only the summation channel is substantially saved. By having a small or zero gain along this difference direction, we do not transmit mostly the noise in this channel, saving the output cost, while not losing much information here, since there is very little information left in this channel when the noise is too high. Let's again look at an example. Here the input signal is much weaker than the noise, so the information available at the input stage is quite small, 0.216 bits, of which only about 10% is in the difference channel, because this channel is filled mostly with noise. Without gain control, the extracted information in O is this amount. Okay, it's quite a reduction from the original due to the addition of the encoding noise NO, which is substantial compared to the input signal power, which is quite weak. However, again, only about 10% of this total information is for the difference channel. But if we look at the costs in the two channels are comparable, because most of the costs are spent on noise, which is dominating. Therefore, it's a poor trade-off in the difference channel to spend almost half of the costs for only a tiny fraction of the information extracted. And therefore, it's a good idea to apply gain control, for example, to abandon the difference channel by giving it a zero gain while keeping the summation channel. And therefore, the cost is now reduced, mostly from the difference channel. We still have a baseline cost of 1 that's more or less because the encoding noise in that channel is still there. But we save substantially by not transmitting the input noise. Meanwhile, the information from the summation channel is still transmitted, so we keep most of the information compared to no gain control. So therefore, appropriate gain control again helps us to achieve cost saving without losing too much information. Therefore, gain control has very different strategies in different signal-to-noise regions. With strong signal, we do decoloration, even whitening. The contrast signal is enhanced. This helps us to see stereo depths more easily. With weaker signal, we do smoothing. The contrast signal is downplayed or even omitted. This should make seeing depths difficult in dim light, especially when you do not have other cues, such as perspective cues, to help you.